Hello and welcome to section 4.5, which is a continuation of our curve sketching skills. And these are more difficult problems where finding f prime and f double prime are a bit more complicated, and we need to use our interval testing to find our increasing, decreasing, max, mins, concavity, and points of inflection. So just a couple reminders. Domain you can find using your regular math 10, 11, 12 methods as with intercepts. A reminder, there are two types of symmetry. Okay? Something is an odd function, which has symmetry across the origin. If f of negative x equals negative f of x, so you need to plug negative x into your function and see if you get the negative version of the original function. Something has even symmetry or symmetry across the y-axis. If f of negative x equals f of x. So if you plug negative x into your function and you get your original function back out, that would be an even function which has symmetry across the y-axis. Intervals of increase or decrease, you need f prime. Increasing is where f prime is greater than 0. Decreasing is where f prime is less than 0. Your max or min values, you're looking for where does f prime equal 0 or does not exist, and you need to find a change in sign. So a max will be a change in sign from positive to negative, and a minimum will be a change in sign from negative to positive. So f prime equals 0 or does not exist, and change in sign of f prime. Your concavity was looking at f double prime. If f double prime is positive, you're concave up. If f double prime is negative, you're concave down. You have inflection points where f double prime equals 0 or does not exist, and you have a change in concavity. So concave up is f double prime greater than 0. Concave down is f double prime less than 0. And inflection points is f double prime equals 0 or does not exist, and a change in sign of f double prime. Okay, so when we're trying to sketch a curve of some of these more difficult problems, we're going to go through each of these pieces, A through G, find all these intervals. What's our domain? Where are our intercepts? What type of symmetry? Do we have any asymptotes? Where are we increasing, decreasing, max, min values, concavity? And all of these will help us sketch the function. Now, you could make a table of values, pre-calculus 12 or math 12 style, but the goal here is to be using calculus to sketch the curves, okay? So if we're going to want to sketch this curve, we're going to go through A through G. Now, in order to do all these things, we're going to need f prime and f double prime at some point. So I'm going to start by finding those so that I have them ready to use. So f prime for this, we need quotient law. So the derivative of the top is 1 times the bottom minus the top, which is x, times the derivative of the bottom, which is 2x, all over the bottom squared. So if we simplify this, we get x squared minus 1 minus 2x squared, all over x minus 1 all squared. And this means that f prime is equal to negative x squared minus 1 over x minus 1 squared. You could factor a negative out on the top, but it's not necessary because nothing will cancel on the bottom anyways. Okay. Now we need f double prime. We're going to need quotient law again. So the derivative of the top this time is negative 2x times the bottom. Oh, I just noticed an error. I forgot my x squared in my brackets there. Sorry, go back and fix that. Okay, so the bottom should be x squared minus 1 all squared minus the top, which is negative x squared minus 1, times the derivative of the bottom. You need chain rule for that. So you should get 2 times x minus 1 to the power of 1 times 2x all over x squared minus 1 squared. Now, many people will start expanding the top, collecting their like terms, but hopefully you recognize that we have an x squared minus 1 in all of our terms, so we can cancel one of each of these out. Now, on the bottom, we should have x squared minus 1 squared all squared here, which would simplify to be x squared minus 1 to the 4th. So you can fix that first, or we can start canceling out first. So there's an x squared minus 1 on the top in all the terms, so each of these are going to cancel out. And instead of being to the 4 here, this is going to be cubed. Now on the top, the left term, I get negative 2x cubed plus 2x minus negative x squared minus 1 to the 4x all over x squared minus 1 cubed. This gives us negative 2x cubed plus 2x plus 4x cubed plus 4x all over x squared minus 1 cubed. And this will give us 2x cubed plus 6x all over x squared minus 1 cubed. Now again, if you want, you can factor a 2x out of the top. So you can say this is 2x times x squared plus 3 all over x squared minus 1 cubed if you'd like. So we're going to need these later to find increase, decrease, concavity, max, mins, and points of inflection. Okay. If I went too fast there, feel free to pause, scroll back, and replay. So your domain, we can just look at the original function and find any non-permissible values. So hopefully we notice on the bottom, we can't have x squared minus 1 equal to 0, which means x can't equal plus or minus 1. Depending on what notation you've been using, you might also write this as x such that x can't equal plus or minus 1. X is an element of all real numbers, something like that. You might also use interval notation, but x cannot be plus or minus 1. Intercepts, reminder that your y-intercept happens when x is 0. So if y is equal to x over x squared minus 1, your y-intercept will happen at 0 over 0 squared minus 1, which is 0. So your y-intercept is 0. A reminder that your x-intercept happens when y is 0. So you'd have 0 equals x over x squared minus 1, or 0 equals x. So your x and y intercept are both at 0. What this means is our intercept is at the origin. So we have x can't be plus or minus 1. We have an intercept at the origin. Our symmetry, we're looking for f of negative x. Does it equal f of x, or does it equal negative f of x, or neither? So our f of x is x over x squared minus 1. F of negative x would be negative x over negative x squared minus 1, which is negative x over x squared minus 1. So the question is, does this equal itself? No, obviously this is not the same as this, but this does equal negative x over x squared minus 1, which is negative f of x. Therefore, this is an odd function, and our symmetry is about the origin. If it didn't equal either, we would say neither, there is no symmetry. Now, our domain here is going to help us with our asymptotes. Remember, for a rational function, your asymptotes happen if you have no common factors between the numerator and the denominator. We had no common factors here between the numerator and denominator. Therefore, our non-permissible values will result in asymptotes. So you have vertical asymptotes at x equals plus or minus 1. And then also a reminder from Math 12, your horizontal asymptotes are at 0 if the numerator has a smaller degree than the denominator. If our numerator and our denominator have the same degree, your asymptote is at the ratio of the coefficients of the highest power. So for example, if I have something like y equals 3x squared plus 2 over 5x squared minus 3x plus 4, a horizontal asymptote would be at y equals 3 over 5, because the highest power on both is an x squared. Our degrees are equal, and the ratio of the coefficients is 3 over 5. Okay? And that will happen for any rational that has the same degree on the top and the bottom. If the degree on the top is bigger than the bottom, you don't have a horizontal asymptote, you have an oblique asymptote, or a linear, like a straight diagonal line. So if you have the degree of the top is smaller than the degree of the bottom, we have an asymptote at y equals 0. Now, from way back in your limits chapter, you would have also looked at limits that help you find asymptotes. If you don't remember this stuff from Math 12, you can use that as well. Reminder, if you have a limit as x approaches plus or minus infinity of your function equals some number L, then you have a horizontal asymptote at y equals L. If you have the limit as x approaches some number A of f of x equals plus or minus infinity, then you have a vertical asymptote at x equals A. So you can take a look and say, okay, is there anywhere I approach for this function? If x approaches a certain number, I'm going to get an answer of infinity or negative infinity. That would give me my vertical asymptotes. Or if x approaches infinity or negative infinity, will this converge on a single number? So you can use calculus here to figure out your asymptotes as well. For intervals of increase, decrease, remember we need f prime. So we had, from the front of our notes, we had that f prime was equal to negative x squared minus 1 over x squared minus 1 squared. We're going to do these two things together because they both have f prime. So what I want to know is, where does f prime equal 0 or does not exist? Then I'm going to use that to figure out where I'm increasing or decreasing, and I can use that to help me find my max mins. So f prime is going to equal 0 if the top of the fraction is 0, which means x squared would have to equal negative 1, and this is not possible. So that means f prime is never 0. F prime does not exist if the denominator equals 0. This would happen if x squared minus 1 was 0, or if x was plus or minus 1. So what this means, if I do my interval testing for f prime, I have negative 1 and 1, and f prime is equal to 0 in these two places. Or sorry, f prime does not exist in these two places. F prime never equals 0. And to find increase or decrease, what I want to know is, in these intervals here, am I positive or negative? If I'm positive, I'm increasing. And if I'm negative, then my function is decreasing. If I switch from increasing to decreasing at either of these points, I can figure out if I have a max or a min. Okay. So what I'm going to do is I am going to test some values. So I'm going to test something where f prime is less than -1, something like -2. Some people find it handy to make themselves a little chart because f prime is so gross. Okay. Some people find it helpful to do interval and then do the numerator, denominator, and therefore all of f prime. Is it positive or negative? So our numerator here is -x² - 1. Our denominator is x² - 1 squared. Our first interval is x is less than -1. Our next interval would be between -1 and 1. And our last interval is greater than 1. So if I think about this, if I put in something less than -1, something like say -5, my numerator is going to be negative. My denominator, I'm squaring at the end, so no matter what I do, my denominator is positive. If I take a negative number and divide it by a positive number, I get a negative answer. In my next interval, I could try something like, say, 0. If I put 0 in my numerator, I get -1, negative answer. If I put 0 in my denominator, I'm squaring at the end. No matter what I do, I'm going to get a positive answer. And I'm in the same situation I was before for my previous interval. I'm negative again. Last interval, if I try something like 10 or 5 or 4, if I plug that into my numerator, I'm going to get a negative number. I have something like -4² - 1. In my denominator, again, no matter what I do, I'm positive, so I'm back in the same situation. So this means in all three intervals, f prime is negative. What that means is for f, my original function, I'm decreasing, decreasing, decreasing. This means I'm decreasing everywhere. I'm never increasing. And because my f prime is never switching signs, there is no max or min. What that would mean, if there's no max or min on a function, that means that this thing must be going to infinity and negative infinity. So it's never increasing, this function. Okay. For concavity and points of inflection, we're looking at f double prime. F double prime for us was 2x cubed plus 6x over x² - 1 cubed. Again, concavity, we're looking at concave up, f double prime is positive. Concave down, f double prime is negative. We need when f double prime equals 0 or does not exist for points of inflection. So f double prime equals 0 if 2x cubed plus 6x equals 0, or 2x times x² plus 3 equals 0, which means either x equals 0 or x² equals -root or -3. This is not possible. So I just have x equals 0. Then I would have f double prime does not exist if x² - 1 cubed is 0. If the denominator of a fraction is 0, then that fraction does not exist. And we know that this happens if x equals plus or minus 1 from our previous fractions as well. We had the same answer there. So we can do something similar that we just did for our concavity. Now, again, you can make a chart if you want because of this lovely fraction set here, or you can just do an interval test. It's up to you. If you can do it in your head, that's fine. So I've got f double prime, and this time I've got -1, 0, and 1. So I have 4 intervals this time. And I'm going to want to see what happens to f of x as I go through this. So f double prime was 0 here and does not exist at -1 and 1. Again, if you found the chart helpful, You can do a chart for interval, numerator, denominator. This time we'd have f double prime. You can break the numerator into two chunks too, if you find that helpful. So our numerator was 2x cubed plus 6x. Our denominator was x squared minus 1 cubed. Our first interval was less than -1. Then we were between -1 and 0, then 0 to 1, and then bigger than 1. So if I plug something negative into the numerator, I'm going to get a negative number because a negative number cubed is negative, and 6 times a negative number will be negative, so you're adding two negatives together. If I plug something less than -1 into my denominator, I'm going to be squaring that. So if I had something like, say, -5, I would have -5 squared minus 1, which is a positive number, and then cubing that. So that's going to be positive, which makes f double prime negative. So that means this first interval here is negative, which makes my f of x concave down. If I plug in something between -1 and 0, again, my numerator will be negative. My denominator now, though, what will happen in the brackets is if I take something like -0.5 and I square it, I get a positive number, but that positive number minus 1 will give us a negative number. Negative number cubed gives us a negative, which means f double prime is positive. That makes this second interval positive and concave up between -1 and 0. Between 0 and 1, again, okay, so for between 0 and 1, we might choose something like 0.5. We cube that and add 6 times 0.5, we're going to get a positive answer. If we square that and subtract 1, we get something negative. Negative cubed is a negative. This is a negative, which means 0 to 1, we're negative f double prime, which means we're back to concave down again. Now, if x is bigger than 1, we're going to get a positive numerator, positive denominator, positive f double prime. So you can plug in something like 10 to try that out if you'd like. Back to concave up. Now remember, with an inflection point, we can't have an inflection point if the point didn't exist on the graph in the first place. So right here at 0 is our inflection point. We don't have an inflection point at -1 and 1, even though we're changing concavity here. We don't have an inflection point because f, our original function f, did not exist at 1 or -1 either. So even though our f double prime algebraically has said, hey, look, we should be switching concavity at these two values, we should have inflection points. We don't, because on our original function, these do not exist. They're asymptotes, and you can't have a point on an asymptote. Okay? So we're going to use all this information to try and sketch this thing. Okay. So we said we had an asymptote at y equals 0. We had an asymptote at x equals -1 and x equals 1. We had our intercept at the origin. We know we are concave down when x is less than -1, but we are also decreasing. So our options when x is less than -1 is we can either go in here or here. Now, because we're concave down, that's what this one looks like here, and we're decreasing. Remember, we're decreasing everywhere, so we can't possibly be that top section there. In between -1 and 1, remember, we're supposed to be decreasing everywhere, but you can see that we're passing through the origin, changing concavity. To the left, we're supposed to be concave up, so we obviously can't be down here because that would be increasing and concave down. So over here, we're going to have to be concave up and decreasing. And then to the right of this, we're supposed to be concave down and still decreasing. So something like this. In our last two sections here, again, we're either here or here. And since we're supposed to be concave up and we're still supposed to be decreasing, we would have to be in this upper section here. If I was in this lower section, that would be actually an increasing portion. So these are quite onerous questions. They're quite tedious. Okay? These are all skills that you have from previous chapters. We're just putting them all together. Okay? But they can take quite a long time to do. And when you're finding your F prime and your F double prime, if you make a mistake on either of those, then you could end up with quite a few errors in your intervals of increase, decrease, concavity, max, min, and inflection points. So just be really careful when you're finding your F prime and your F double prime. And that is it for 4.5.